We're going to go through this question in two different ways. First up, I'm going to talk about a method that's very elegant and quick, but there's some subtleties to it. So I didn't think to do it this way, but I can appreciate it afterwards. We've got our 4 digits. Now we know the first digit must be a 1 for part 1. Okay, because 2000 is not an ascending number, so it's basically all the numbers from 1000 to 1999. Now clearly 0 cannot be in our number, and also 1 cannot be in our number again. It's already there as the first digit. So I can ignore these two, and there's not going to be any repeats either. This is what I mean by the subtleties. These are things to like figure out as we're doing it. Because what that means is that there are 8 options. Forget the ascending part for now. There's just 8 possibilities for the second digit from 2 to 9. And then after we've picked one of them, there's going to be 7 possibilities for the third digit. And the product rule of counting says we're going to times them, because for every second digit, there are 7 third digits, for example. So we do 8 times 7. In a similar way, we'll then times by 6 for the fourth digit. Okay, there's again one fewer option. So that tells us how many numbers we can make that start with a 1, and the second digit is then 2 or more. Now, when we consider this 3-digit number, there are 3 ways of ordering A, B, C. In fact, let me write them down. So that one, and CBA, CAB, BAC, BCA. We say there are 3 factorial ways, in fact, because there's 3 options for the first, then 2 for the second, then 1. And it's worth kind of looking into this sort of maths and arrangements. Okay, now why am I going down this route? Because when we have 3 numbers, 3 digits, and we know they're all different, there's only one that is going to be ascending. It will necessarily be ascending. It has to, it will continue to increase. The other ones, they might decrease, or they might increase and then decrease, or decrease and then increase. I suppose maybe I could do some numbers for this. So let's say we've got 1, 2, 4. As soon as then, it would be 1, 4, and 2, and then it would be 4, 2, 1, 4, 1, 2, 2, 1, 4, 2, 4, 1. So you see, just this one here that is ascending. What that means is that when I work out my 8 times 7 times 6 options, I've got all of the possibilities, and if I divide through for every single like triplet that we can get, I need to divide through by 6 to get the triplet that is ascending. So I then cancel out the 6's, and then we get 56. Okay, I did say it was subtle, I said it was quick, but that is what's going on. Part 2 then follows along very similar lines. So now we don't have any restriction on the first digit except, well, it could be 1, but it could be 2 or 3 as well, which means there's going to be 9 options for the first digit. I just can't include 0. And then there's going to be 8 for the second. Remember, I'm not allowing any repeats, then times by 7, then times by 6. This is the total number of ways that I can put 4 digits down where the first digit isn't a 0 and none of the rest are zeros either, and none of them are being repeated, if that makes sense. Now this time for my A, B, C, D, there's actually 4 factorial or 24 ways of arranging. So for a given kind of set of digits here, there's only, like let's say I have 1, 7, 2, 3. There's only there's 24 ways of arranging this, but there's only one way when it will be ascending, 1, 2, 3, 7. So again, I've counted every single possibility of digit, and I've got these like groups of 4, but I'm going to need to divide by 24 to get the ones that are ascending. So 24 will cancel partially with the 8, leaving me a 3 on the bottom. Then the 3 will partially cancel, let's say, with the 9. So I'm going to end up with 8, let's do 21 times 6, which gives 126. All right, really nice approach, although there's a lot to think about, I think, for this approach. Let's take a look at another approach for this question. This is more brute force. It's not like looking at every possibility, but it systematically kind of works out how many there are for certain conditions. Anyway, let me show you. So I'm going to focus first on part one. Part one is a good build up for this. So 4 digits, we know the first one's going to be 1. Again, we can ignore the 2000. Then we've got A, B, C. As I implied before, A must actually be between 2 and 7. And B must be between 3 and 8. Actually, I don't think I mentioned that before, but yeah, sorry. So this is, I said I said A has to be between 2 and 9, in fact, originally, but now I'm recognizing that B is going to have to be greater than it. So there's no way that A could equal 8, because then B and C wouldn't both be greater than A and themselves be ascending. And then C is going to be between 4 and 9. Okay, then we're going to do it case by case. If A is equal to 7, then there's just one option. B is 8 and C is 9. So I'm going to keep a running total. If A is 6, then I could have B equaling 7, which means that C could equal 8 or 9, which gives me two options. Or B could equal 8, which gets me the one option I had before. So I'm going to have 3. A equaling 5, I could have B equaling 6, and then C could equal 7, 8, or 9. So I've got like a 3 here. If B is equal to 7, I've got my same two options I had there. And then B equaling 8, I've got my one option. So overall, I'm going to have 6. And you can kind of see a little pattern emerging. For A equals 4, I can have B equals 5, which is going to lead to 4 possibilities for C. And then I'm going to get 3, 2, 1, just like before. So it's going to take me to 10. And you might recognize these are actually the triangle numbers. A equaling 3. I'm going to have all the ones from before, the 10, but now I've got an extra B equals 4, which gives another 5 possibilities. So that's going to get me to 15. And then finally, A equals 2, I'm going to have the 15, but then I'm going to have an extra B equals 3, which is going to give me another 6. So 21 in total. And that is it. That is the, kind of got briefer as I went down, but I still tried to explain my logic. And in the real thing, just make sure you explain what you're doing. But if we add these up, got 10, 20, 35, 55, 56. Same answer as for the first method I went through. And this method does lend itself well to part two as well. So this time, I've obviously got different values of A. Now we know when A is equal to 1, oh sorry, I'll relabel it. Okay, I'll use A, B, C here as before, but now I'll say that this is D. Okay, so D is equal to 1. I just want to I don't want to start changing what A is. A is the second digit, and it was for part 1. So when D is equal to 1, we already know that there are 56 possibilities because this is what we did in part 1. When D is equal to 2, I just don't get the A is equal to 2 possibilities. So I need to do 56 minus 21, which gives me 35. So this actually works very quickly. Let me just explain that a little bit again, actually, because that, like the whole method kind of hinges on this. So I know there are 56 ways when D is equal to 1. And that included A equaling 2. But when D is equal to 2, I get the same answers, except I'm just not going to have these 21. That's why I subtracted it from the overall amount. So 35. And then I can just basically keep subtracting. So for D equals 3, I'm going to additionally subtract the 15. So that will give me 20. D equaling 4, subtract the 10, so I get 10. And then I'm going to subtract 6, 3, and 1. So 4, 1. Actually, D equaling 7 would be 0 because I can't actually have it equal to 7. but sorry, I was just following on with the pattern. So now I just need to add these up and I'll have my total. Again, just make sure you explain, what you're doing. I've kind of tried to do it in words here, but I would be writing down a lot more in the real thing. So 56 plus 35, 91. I might keep track of it a little bit. And then I've got 30, 35, which again takes me to 126. Nice.